Ah,
Sí, pero
ya.
Mira, acá estamos, son Ecuador.
Yes.
yo
No,
almorcé recién.
mira, acá
En la
estamos.
reunión, después me quedé trabajando, entonces quiero almorzar recién. Son las tardes, entonces.
Like Nunokawa.
Muchos
Hiroshi.
años.
Hiroshi was
Todo bien.
also Minakata.
Sí, de hecho, hubiera bueno, yo creo.
I have a
Ah, sí,
student,
sí,
but
sí.
I was in
Mañana
the same
domingo, pero la
university.
noche-
Ecuador.
Es que mañana
Ahí estamos. La llamada.
Sonido se escucha.
Sí, sí, sí.
Toca probarlo.
Es que es sencillo, pero tengo confianza de que funciona. Los micrófonos están abiertos, ya los desmuteé de Zoom a través de la tele y ahí arriba, si te fijas, hay un rec de la grabación.
Está grabando.
Y ya no tienen nada que hacer. Los participantes solo entran y lo único que van a ver es que como se meten y si tienen el micrófono abierto van a aparecer ahí abajo. Porque la cosa es Zoom, que toma la prioridad del que está hablando en el momento.
Cierto.
Pero nada que adultos responsables no puedan decir, te puedes mutear. Porque a esta altura ya no hay como mucho más que tengan que hacer, ya estaría todo listo. Está todo-
No hay una configuración de que todo el mundo que entre muteado.
Todos entran muteados.
Ya si lo abren.
Sí, es que cuando te preguntas si la sala previa, que te dice, ¿quieres meterte con el sonido activado, todo eso? Ahí los profes van y le dan al un mute. Y ahí toma como super sí el tema de que Zoom te obliga y ellos entran con el no, quiero hablar.
Okay.
Es como lo del video, porque de repente algunos entran sin video y después lo prenden. Es porque cuando antes entran, les dice el preview, quieren prender tu video y lo apagan. Ese es como el gran pero, así que por eso estamos un poco a la merced de cómo entre la persona.
Hágale, sí, tranquilo.
El volumen.
7 de julio, ¿cierto?
Sí, lo único.
Hoy es 10.
El volumen está. Oh, sí. Adelante. Tienes que hacer clic. Ese es el único. Ahí está. Lo bueno es que ni siquiera tienes que cambiar del tema. Ahí, duplicar, compartir, controlar. Listo. Ahora sí. Ahí está.
Todavía faltan 5.
Sí, igual cualquier cosa, sé que tienen mi número para avisarme cualquier cosa, pero estaría listo y sin problemas.
Vale, muchas gracias.
Voy a tomar una foto.
Por favor, ya se me olvida. Ay, es importante. Por aquí, ¿cierto? Se llama bien. Proof that I came and gave a seminar. And it's me, it's not Photoshop. Nobody has a newspaper with the, when you are sequestered, you have the newspaper, just people say, yeah, it's today, the guy is alive.
Más tarde no sé qué es en España, ¿no? Son 5 horas. Usted me parece en Brasil. Ah, en Brasil. Y son 3 horas. O la misma hora acá.
Una hora. Una hora más tarde, Brasil, ahorita.
Sí.
Una hora más tarde.
Sí, yo podría hablar. Pero no, lo de las 2, ¿sí? Aparte de las 2 tenemos pero esa hora podría ser. ¿Ves de Alfonso? ¿De Alfonso? Ah, bueno, sí. Alfonso se iba o... Yo partí sí, pues sí, yo me lo diría, pero probablemente llegaré con algo de retraso. Luego que estoy yendo a reuniones a la hora para almorzar. Pero a las 2:30. 2:30, sería media hora. Yo podría estar solamente media hora porque a las 3 tengo que estar en una defensa de tesis como estudiante de César, porque soy miembro de la comisión y se va a terminar a las 4:30. Y a las 4:30, 4:40. A las 5 los estudiantes, así que más bueno. 2:30. 2:30, 2:30, 2:20, por ahí. 2:30. Hola, ¿cómo estás? Bien, ¿verdad? Bien, gracias. ¿Tienes mi tiempo? Ah. ¿Tú podés mañana a las 2:30? Sí. Aunque no sé, para Rocío sería. Ah, no, está bien, sería 8 horas, segunda defensa. Ay, ya de montar. Esperemos, Claudio. Sí, porque él sabe. Sí, esperamos unos 5 minutos.
Online no hay nadie, ¿cierto? Todavía.
Daniel lo puso en
Ya está automático.
sí, que
Sin sala
entran
de espera,
automáticamente.
ya.
Revisemos mejor.
Solo
Sí,
iba a
revisamos
entrar,
si
creo
acaso.
que César, ¿no fue que pidió César? Pero en
Yo me
principio...
imagino que César también se va a conectar, o si César no se conecta, se conecta.
Sí, porque ya son las 3, ¿no? Son las 3, ya debería...
Sí, se me perdió el mouse.
Supongo
No sé
que...
si el público ahí en la parte de Zoom. ¿El público? Ahí el inicio, ¿no?
No,
Perdón. Disculpa.
tranquilo.
Acá. Ah, pero no se ve el.
Tienes que saber, creo que tienes que dejar de compartir primero.
No,
Entonces...
sí está compartiendo. Pero no sé dónde se ven los.
Por eso, para verlos, creo que deberías dejar de compartir.
Es que no sale ni el. Es que sale, a veces
Es que las herramientas, de pronto quito las herramientas para que no se vean.
Ah, las quitó, ¿cierto?
Sí, las quitó del... No están visibles las herramientas, sí.
Esto está con volumen, perciable.
Sí, ahí está con volumen.
No, yo no sé, eso no sé qué quería vender.
Sí, parece que está bien.
No, sí, yo creo que está.
Déjame ver si ya está. No, ya está puesto.
Yo creo que sí, porque son las 3:02. ¿Comenzamos? Sí, de entonces.
Good afternoon. We are very happy to have here Professor David Banega Forero, who is an internationally recognized expert in neutrino physics. He is a member of the DUM collaboration. He is a professor from the University of Medellin, and today Professor David Banega Forero will talk us about non-standard neutrino oscillation, days of future past. You can start, David.
Okay, thank you, Antonio, and thank you all for coming. Thank you, Carolina, for inviting me. I'm here because Carolina invited me to Chile, so I'm first time in Santa Maria, and very happy to be here, although it's a bit cold. Okay, so let's start. So in this talk, I will talk about some standard and non-standard interaction, and by non-standard, I mean that can be anything beyond the standard model, not only NSIs. Okay, this is my name, author name, and my email if you want to contact me. Okay. So the concept of a neutrino oscillation experiment from a theorist point of view is quite simple. You need an intense neutrino source, a massive far detector, and you optimized the distance so you can properly have oscillations. And modern experiments also include a near detector. So the near detector is very good for reducing systematics, mainly attached to the flux, neutrino flux at the source. And then you let the experiment run for several years. And this depends, of course, of your physics goals, and mainly the main limiting factor of the running time will be funding. So you need to convince the funding agencies that the physics you are going to do is something rewarding, so they can give you money and let you run for several years. So, okay, this is the source. So there are many neutrino sources, natural and man-made, spanning several orders of magnitude, like 74 orders of magnitude. Starting from the low energy part, we have the cosmological, solar, terrestrial, and the high energy part, atmospheric and extragalactic sources. However, for neutrino oscillations, we only there is a small window around the 1 MeV to hundreds of GeV that I mean, neutrino experiments will be sensitive to these neutrinos produced in this energy window. So it's a small window in this large landscape. And then I said that you need a high intensity neutrino source, and you need also neutrino detectors. So there are several technologies available. You can recognize two of the experimental collaborations that were awarded with the Nobel Prize in 2015 for the discovery of neutrino oscillations. And still, the experiment T2K is using the same supercambio candidate detector. So I put the sources here so they can detect, these technologies can detect reactor, atmospheric, solar, and accelerator neutrinos. And probably what is good to see that some people here are at scale. So the scale, for comparison, there is some person here and some person here. So basically, the message is that you need a massive, very massive detector in order to have some statistics so you can detect some number of neutrinos. And from one side, you have the source, detectors, and you have to optimize the baseline to see oscillations. So what is the oscillation about? So there is one paradigm that is the three active neutrino paradigm. So we know that we have three active neutrinos, and you can have several other that are not active. But in the minimal scenario or scheme, you have only three active neutrinos. So you couple with only three right-handed neutrinos, and you form a 3x3 lepton mixing matrix that you can assume is unitary. And you can parameterize it in this way. That is a standard way to parameterize the lepton mixing matrix. 3 mixing angles, one CPU relating phase that it comes from the Jaskok invariant, and 2 mass square differences. So if you have 3 active neutrinos and 2 mass square difference, then you have 2 possible orderings. So the solar splitting is living here, and the atmospheric is the difference between the 1 or the 2 and the 3, right? So you can have the opposite order where the third neutrino is in the lowest, its mass is the lowest one. And we don't know yet what is the correct ordering. So we have here, I have highlighted somehow what are the unknowns, the known unknowns in the neutrino sector. There are many other phases that doesn't appear here that are the Majorana. In the case neutrinos are of the Majorana type, there are 2 additional phases here that I haven't included in the parameterization because neutrino oscillations are not sensitive to these Majorana phases. Neither is sensitive to the absolute neutrino mass. So for this, you need other searches to account for the absolute neutrino mass. Mainly, the lab experiments can prove through beta decay, the endpoint of the spectrum will be sensitive to the neutrino mass. So you can put some bound here. And also, in an indirect way, a standard cosmology can put a constraint based on the sum of neutrino masses. So if you collect all the experiments classified by source that have seen neutrino flavor transitions, so all of these names here corresponds to different sources. For instance, we have in this list solar experiments that are the old experiments and superchemical that is still running. And Camlan, that is not running anymore, but it's a reactor. And you have the atmospheric sector, you have the accelerator sector, and you have the reactor sector. So this is mainly because you can test, these experiments see or measure oscillations driven by the solar mass, square mass difference. And these other 3 sectors see oscillations based mainly driven by the atmospheric neutrino mass splitting. So this is to say that, okay, so if you want to improve precision, then you need to go to an experiment where you can control many things. One of the things you can control is, of course, the source. And this can be done in accelerator experiments, or you can build several mirror detectors or multi-detector experiment to reduce systematics. So if you plan to improve your knowledge and account for and improve the precision, then you need to go to the this next generation experiments. And this is the reason why you go for accelerator and reactor, because you can control the source and put many detectors. So this is the current, more or less the current knowledge of the oscillation neutrino parameters. And here is quoted what is the precision we have reached so far. So is the order, we are in the order of 1 to 6% precision at the moment. And the less known parameter that there are several information here. So the normal ordering is in blue and the inverted is the magenta, right? So there is some preference for normal ordering, although not a big preference. The preference is on the order of 2.5 sigmas, right? And we don't know yet if there is CPU violation in the lepton sector. Still, there is some exclusion of almost half of the parameter space in the case of inverse ordering. But still in normal ordering, that is the preferred order here, the preferred ordering, CP conserving values are still allowed within 3 sigma. So we don't know yet if there is CP violation in the lepton sector. So we need future experiments also for to answer these questions. If there is CPU violation in the lepton sector, and what is the ordering that neutrinos will follow, and to improve precision in this parameter that is the less precise one. So if you plot the mixing angles in the 3 sigma range, and I put a dot in the best fit value. So one of the old questions has been if this mixing pattern can be explained somehow through some symmetry, right? Because before theta 13 was mentioned in 2012, there were many models that were motivated by discrete symmetries where you can explain the mixing pattern. But after the measurement of the reactor mixing angle, these models are not so okay. I mean, you can tweak them and through some corrections still explain somehow this mixing pattern. So this is like a kind of open question. So where we stand so far? So we know we don't know if there is a CPU violation. We don't know the ordering. There is some preference for normal ordering with low significance. We don't know yet what is the octant of the atmospheric mixing angle, if it is maximal or if it is not maximal, what is the octant? Is the lower or is the upper octant? And this has been problematic for precision. The precision of all the parameters that have been measured is around 1 to 6%. So basically, this list includes all the current known unknowns in the neutrino sector. So all the future experiments, the standard oscillation neutrino program is motivated by this list that is here, right? We want to know all these things. So the good thing is that we need some experiments to improve the precision. And this will bring us to the second part of my talk. The second part of my talk is that, okay, you have some approved experiments, already approved, like Dune, Hyper-K, Juno, that will bring some light into the what if there is CPU violation, they will be able to measure it. To improve the precision in the solar sector, to establish what is the correct mass ordering, and to measure precisely the less known parameter, the less precise parameter, right? But this is not the full story. Mainly for a theorist, the good thing is that if you will have a standard neutrino program that will be very precise, will bring precision to the arena, you want to test other BSM scenarios. So this is the second part of my talk. I will introduce some BSM searches that have already been performed at collaborations and have been in the market for many years. So one of the examples of these BSM scenarios is a generically speaking. So you have different scenarios motivated theoretically or motivated phenomenologically, right? If you pick your favorite theory and you want to include neutrino masses or to explain dark matter and neutrinos, etc., then you will have new extra degrees of freedoms that can impact somehow neutrino oscillations. Or if you have seen in experiments some anomalies, some excess, then you cannot explain through the standard neutrino oscillations, then you can motivate the BSM searches, right? For instance, you can have additional framework states. They can be sterile, but we don't know yet what is the scale of these extra singlets. If you are in the low energy scale, you can talk, and if they are at the EV scale, then you can say that they are the sterile neutrinos that participate in oscillations. But if you are in a high mass scale regime, then you can talk about them like neutral heavy leptons. Some of them you can be produced in beam dam experiments or accelerator experiments. And if they are even heavier, then the only way you can test the presence is through deviation of the unitarity, for instance. You can also have extra dimensions. So there are some models of large extra dimensions where additional neutrino states appear in these theories, and they can imprint. You can have some signatures in neutrino oscillation experiments. Also, neutrinos can have new non-standard neutrinos interactions, and there are several theoretically well-motivated scenarios where you can have even a standard model effective field theory when they appear like dimension 6 operators or higher dimensional operators that will appear at low energies as an effective contact interaction. They will produce some NSIs that will imprint, will appear or have some effects in oscillations. Some other properties you can test if neutrino decay, there is magnetic moment, etc., etc. Violation of symmetry of fundamental symmetries. For example, you can test with neutrinos the CP theorem. You can test deviation from Lorentz invariant. You can test quantum decoherence, and standard quantum decoherence, that is the wave packet decoherence, or non-standard decoherence that is motivated by gravity theories, other theories. And many other things that you can imagine as a theorist, something that can have some signature in neutrino oscillation experiments, so you can try to see if you can search or constrain the parameters of these new theories. So basically, if you have any model that impact any of the 3 stages for a neutrino experiment, so if production, detection, or propagation, then probably you can have some signatures in neutrino oscillation experiments through spectral distortions. So I have done some exercise that is basically I have checked in Inspired what are the papers produced between 2008 to 2025 that have been published by experimental collaborations, neutrino experimental collaborations. And if you do this exercise, you will see that let's say not famous, frequent. The frequent subjects you will find is CP and Lorentz violation, sterile neutrinos, NSI, and Lorentz dimension. So these are more or less the 4 subjects or 5 subjects that experimental collaborations have tried to see in the experiments, and they haven't seen any. So they have put some constraints on all these kind of models, different BSM scenarios, let's say, no models, but BSM scenarios. Mainly, I have done this exercise only for accelerator and reactor experiments, and these are the names. And you will find that are like 25 papers already. And probably the experiment that have been more, have more capabilities to test different BSM scenarios have been Minus. And one of the reasons Minus was able to do this is because it's a wide beam neutrino experiment. And Dune will be a wide beam neutrino experiment more powerful than Minus. So okay, so we have the so-called standard neutrino program to measure all the things we don't know in the standard oscillation case. But then you can in parallel test many other BSM scenarios and try to answer many of these questions that have been in the market for several years. So this is the days of the future past. So all of these have been there for long, and we haven't been able to really say if there is some extra neutrinos, or if neutrinos really decay, or if there is some symmetries to explain the lepton mixing matrix, or any of these questions that have been in the market. So we can try to see if in this next generation experiment we can at least answer one of these questions. So let's talk about a bit of the experiments. So I mentioned Dune. So Dune is a long wavelength experiment. It's aimed to be a megawatt power beam. So it will produce a very intense neutrino beam at Fermilab. In this accelerator, the neutrinos will travel 300 kilometers towards South Dakota to the Sanford facility, and we will study neutrino flavor transition in this far detectors. And what else is important for Dune? So Dune will be, this is the first time we have a very long baseline experiment at the Earth. It's the longest one, and the power is very intense, right? So the competitor, the direct competitor of Dune is the Hyper K that is in J Park. So we have also is an accelerator. Neutrinos are produced at J Park, more or less at the same power, but the difference is the baseline, right? So we have a different baseline. So here the oscillations are more or less, I mean, are in vacuum, and here in matter. So they are in the sense of the interaction with matter are complementary, right? And they can check somehow if someone finds something, so the other one can check it more or less. It's good to have at least more than one experiment. So if they claim they discovered something, so the other one can see and check it. And the other experiment that will be in the market very soon, in fact, I think next year we'll start taking data, is Juno. Juno is a reactor experiment in China, and will be the next generation of Dajabei. So it's also a gigawatt experiment. So you have different neutrinos are produced in these reactors, and they will travel more or less a medium baseline experiment, 53 kilometers, and they will study. They claim they can be sensitive to the mass ordering, but the main goal for neutrino physics, is that they will improve the oscillation, the solar neutrino parameters. So, okay, those are the experiments. So, as an example of how, I mean, we have several BSM scenarios in the market, but in this talk, I will only talk, for the rest of the talk, I will try to address this question. What happens if we have several additional neutrino states, and what can we say about this in future neutrino experiments? So probably you know this, but we have only 3 active neutrinos. There is no more than 3. And the measurement of the C boson with decay, this is a scale. The errors are scaled by are increased by a factor of 10. And you will see that the data points prefer 3 neutrinos. So we know already that we have 3 active neutrinos and no more. So if you want to have additional neutrino states, they have to be sterile. And this sterile oscillation at 1 eV at this scale is mainly motivated by some anomalies, right? So LSND, microon, carbon, all these experiments that have seen some excess that could not be explained in the 3 neutrino picture. They motivate an additional neutrino with a mass square difference set at this scale. This is for one side. From the other side, you can have right-handed neutrinos or many singles that can propagate in an extra dimension, in extra dimensions. And there is a model that is called the vanilla-led model, where you can have several Kaluza-Klein resonances that will, in phenomenological terms, will be like several sterile states. So you can test these 2 kind of scenarios with the same experimental setup. This is what I want to point here. So in the case of the light sterile, so a sterile that is oscillating at the 1 eV scale, all you can have to do is to increase the lepton mixing matrix one row and 1 column to include this extra state. So you will have new mixing angles, the 1,4, the 2,4, and the 3,4. This is the sterile state called S. So you have the active neutrinos plus 1 sterile state, 1 flavor extra state that will mix with the others, right? And you can have new splittings, new mass square differences, new splittings, and at least two CP violating phases that are physical. In these plots, you can see that having a near detector is good to test the sterile hypothesis when the mass square difference is higher than the 1 eV, right? But if the mass square difference is lower and is close to the atmospheric one, then you can have some sensitivity in some signal in the far detector. So in this kind of analysis, it's good to have more than one detector and to do a combined fit of information, spectral information at both detectors, at near and far. One of the smoking gun channels to test this sterile scenario is through the neutral current channel. Why? Because if you have 3 neutrinos, if in the nature there are only 3 active neutrinos, all of them interact with the same coupling with the C boson. So the neutral current is universal and it's the same for the 3. It's flavor blind. But if you have another one that cannot interact with the C, so there is some asymmetry. If you sum up all the contributions from the 3 active, then the probabilities should close to 1. But if you include an extra sterile, then the probabilities cannot close to 1. So this will appear in your detector, let's say in the far detector, as a depletion in the number of, let's say, mu neutrinos. If you start with a bin of mu neutrinos, you can study this channel. This is one of the sterile appearance channel. And through probability conservation, you can test that if this is a departure of the 1 or not. So it's a very easy channel to test this scenario, basically counting neutrinos, right? Counting the total number of flavor neutrinos. And if the total number is less than the number that should be, is because it might happen that there is an sterile state. So we work out this scenario. Okay, before that, those are the exclusion limits from the Dune experiment. These are in the Dune TDR. And of course, as I said before, it depends on the region. So if you are in the parameter space, when you are in the high energy part of the delta M square, then you have some sensitivity that is driven by the near detector. If you are in the lower energy part, the sensitivity is driven by the far detector. Then you have several important information you can use. So basically, a special distortion at the near detector or a special distortion at the far detector. And then you have to simulate your detector, include the probability, and with a set of systematics, you can build these regions. So you are constraining the parameter space that is given by the mass square difference and the mixing angle. In this case, is the mixing between the 2 and 1, including the sterile state, right? This is in this paper we work out what is the contribution of the neutral current only, and neutral current only is sensitive to the other 2 mixing angles that are important in this scenario, that is the mixing 2-4 and the mixing 3-4. So the sterile with the tau and the sterile with the mu. And of course, it depends of the mass square difference. If the regimen is in the low energy regime, there are many cancellations, and then you lose the sensitivity. But if you are in the high energy limit that everybody studies, then you can be very sensitive, especially if it is if the experimental collaboration is able to control systematics below the 5%. So here in this plot, you see that there are many ways to test this parameter space in different experiments, like in a reactor, in an accelerator experiment that is currently running, NOVA, in an atmospheric experiment that is Super K, and the ice cube that is a neutrino telescope, but also is sensitive through ice cube core, sensitive to neutrino oscillations. So all of them are competitive, very competitive in this parameter space. But of course, it depends on the level of the systematics. So the other model I want to show some example of how you can test this at the future neutrino experiments is the LED model. So the LED model is okay. It's a large extra dimension model. You have to include the 3 active neutrinos that they live in the brain, and the extra ones live in the bulk, and they are coupled via the Yukawa couplings, right? So you in this model, neutrino masses are the Dirac one, the Dirac type, and if after the compactification, so if there is some extra dimensions, so more than 4 dimensions, and we live in a 4-dimensional world in principle, so this world is live in the brain, right? And the only contact with the extra dimension is through the Yukawa couplings, right? So there is some mixing between the active and the, let's call, extra singlets. And after compactification, so the compactification details are very, very hard, but there is one scenario where you can have an asymmetric compactification. This means that one of the extra dimensions is larger than the others. This is the scenario where you can have some signal in neutrino oscillation experiments. There are other scenarios of compactification scenarios that will be very convenient for the LHC physics, for instance, because in these experiments, the sensitivity is in the volume of the compactification, and the constraints are very tight, right? So neutrinos will not be competitive to this kind of scenarios, but neutrinos can be very competitive in a scenario where there is one extra dimension that is much larger than the others. So after the compactification, from the 4-dimensional point of view, so from the point of view of the universe we live in 4 dimensions that we can test, what you can see effectively will be right-handed neutrinos that will appear as like an infinite tower of sterile neutrinos. So this is a cartoon of the situation. So you have 3 active neutrinos here, and on top of these 3 active neutrinos, you have several resonances. It's like having the spectrum of the hydrogen atom for each one of the mass states, and then you can have infinite sterile neutrinos, right? Instead of 1, because in the 3+1 scenario that I just talked about, we have only 1 extra. Here we have infinite extra. Okay, so what are the phenomenological consequences? So you have sterile active, sterile mixing, you have new oscillation frequencies, and all of these will distort the neutrino energy spectrum. And then you can test the departures from the standard case. And if you don't discover anything, then you can put some stringent limits on some of these infinite tower of sterile neutrino states. So let's see how it works. If you compute the probability in this model, the vacuum probability is very simple. So you have a correction to the mixing and a correction to the splittings, because you have infinite. In principle, n can be 0 to infinite. But of course, you know, okay, the neutrinos are of Dirac type. So you have 3 Dirac neutrino masses and one parameter that will account for the compactification radius. And the idea is that you can, with neutrino oscillation experiments, you can constrain this compactification radius. What you know is that when n is very small, so it's 0, so you have to recover the standard oscillation physics. So when you are here, so the splitting between these neutrinos have to explain the solar and the atmospheric neutrino mass square differences, right? So you have all the information in the lower n. This is what you have to account for. Then you can parameterize the neutrino mass in terms of the absolute neutrino mass. And then you have only 2 parameters. You have a model with infinite sterile states that you can account with 2 parameters. The other one, you have 1 sterile state, and you need like 3 mixing angles, 2 phases, and 1 splitting. So like 6 parameters extra, right? So it's kind of weird, right? But let's see how it works. So if you include the sterile states at the short baseline, what you see is this is the black line is the standard case. You will not see any oscillation, right? Because it's in the near detector, you don't see any standard oscillation. So it's a horizontal line. In the LED model, you will see different resonances, but since your experiments have a finite energy resolution, you cannot resolve all of these details. So what you see is the green line. And the green line is very different to the black line. So with the near detector, you will be able to be sensitive and to constrain this model with extra dimensions. Let's go to the far detector. If you do the same exercise in the far detector, you have the disappearance probability. The black line is the standard 3 neutrino case. The red one is what your model predicts, but since you have a finite energy resolution, what you can see is somehow of some kind of modulation. So there are many oscillations happening on top of the main oscillation, but you cannot resolve all of them. So you just resolve this kind of modulation. And if you have very good, if your experiment have very good energy resolution, you are able to reconstruct to tell the difference between this bump and this other bump, right? And in any case, the difference between the black line and the green line is not, you can see it by eye, so you can have some sensitivity from this, from the dim far detector. Okay, so what happens if this n goes to infinity? In these plots, the number of modes are like 5. So if you start increasing the modes, you will have many more oscillations on top of the oscillations. So many spy-like features that you cannot resolve. So at the end, you have a model with infinite states, but your experiments will only be able to see up to some number of states, right? So in practical sense, you don't need to diagonalize an infinite matrix, you diagonalize a finite one. So after all the simulation of the experiment and put all the and put the oscillation probability and account for matter effects, include all the systematics, then you can constrain the parameter space. So the parameter space you can constrain is the absolute neutrino mass, and you can constrain in the low energy part of the absolute neutrino mass, you can constrain, you can provide a constraint on R that is very safe, because if you put the constraint here, it's too constrained, right? And depends on the mass. But if you want to be very conservative, then you can put your limit around here. So these are sensitivity curves. The more standard 3 neutrino oscillation point lives here, right? When M's go, when R, the compactification radius go to 0. So what you are allowed to say, the parameter space that is allowed is the one that is below the curves, and what is somehow excluded, I say excluded because it's not data, it's sensitivity, right? So what is more or less excluded lives here. So what you see by the comparison between the two lines, so the red dashed line is minus. Minus is the only experiment that has that was able to constrain the compactification radius in this kind of large extra dimension model, asymmetric model, and their limit is even better than the sensitivity. This is the sensitivity, and their constraint is like here, 0.5 micrometers. But since we are comparing apples to apples, so I need to compare sensitivity to sensitivity. So this is the black line, the dark line, full line is dune sensitivity to this kind of parameter space. So we repeated the same exercise here, but this time not in dune, but in Juno. In Juno plus tau, tau is a near detector for Juno. I guess I'm not sure if it is already approved, but at that time was a proposal, and I think it's approved. And depending again on the systematics, then you can constrain this, what is below, what is above is excluded. So you see that if this experiment claim that they will able to measure the mass hierarchy, they need a precision in the measurement that is around 1%. They have to control the systematics very well. So if this is the case, then the limit coming from Juno is very compatible with the limit with Dune in this large extra dimension models. But if, okay, so more or less the realistic scenario lives here around the green line. So I came to my conclusions. Basically, we have a standard program that is measure what we don't know and to improve what we know in the neutrino sector. And on top of that, we can in parallel test several BSM scenarios that have been in the market in these experiments. We can mainly exploit spectral-like features. We can benefit from the broad energy spectrum of the experiments, or from the energy resolution, or from the discrimination power. And of course, all these things depends on the level of the systematic. So if the experiments are very good to control the systematics below the 5%, they will probably be able to exclude more of the parameter space in the sterile or large dimension case. Of course, we don't know what we appear, so we are like agnostic in the sense that if there is some neutrino oscillations are very good to explain the flavor transition. So if on top of the standard oscillation there are BSM physics, the BSM physics cannot spoil what we know about the standard oscillation. So it has to appear as a subleading effect. This is one option. The other option, there is a completely new thing that we don't know that can show up in the detector. So we have to be careful in the design of the triggers and whatever to see non-standard signals. So this will be harder, right? Of course, there are synergies I haven't talked about. For instance, there are some connections with dark matter and some connection with sevens, coherent elastic neutrino nucleus scattering. This is a process that has been very useful considering some parameter space of BSM scenarios. And recently was discovered, right? It was proposed like in the 70s and measured very recently, and now it's reaching to a point, since they are tabletop experiments that are very economical, they can build many of them with different targets, and then there are many activities in this sevens sector with this process, sevens process. So thank you.
Thank you very much, David, for the very nice talk. Question from the audience? Any questions?
You mentioned about the non-standard interaction, right?
Right.
And as far as I understand, you also mentioned that there is involved effective operators.
Right.
Can you mention a bit more about this? What are the kind of operators? I understand that is a dimension 6 dimension operators, fermion, or fermions.
Yes.
This is the only operator that can explain oscillations
So let me
in non-standard interactions.
see the chart. Yeah, I have a chart. Okay. So you are talking about this. In this talk, I only talk about this scenario, right? Of course, there are many others. So you are asking about this other one. So you can have new neutrino interactions, have been in the market for very long, even from the 80s, because in solar neutrinos, there are no oscillation as flavor transition, and then you can explain the flavor transition through as a non-standard interaction. Okay, but okay, the question is about this first bullet, right? So you have viable NSI model. I mean, viable. Nowadays, you can also work in a scenario in a formalism that is a quantum field theory formalism. as an effective operator. So you can account for all the operators larger than 6. And if they are operators of the form fermion, fermion, neutrino, neutrino, then they will impact the effectively, they will impact the matter potential in neutrino oscillations. So they will appear because the way they are included in general are can be very phenomenological, and it's like you have 4 fermion interaction parameterized by a G Fermi, and then what you account for is a small deviation of G Fermi, an epsilon deviation of G Fermi. This is the NSI parameters. So this implies that your scale should be above the electroweak scale, and they will appear effectively at low energies as these dimensionless parameters epsilon, and these epsilons will account for flavor changing neutral currents in the neutrino sector. And non-universal, it can be also, the interaction can become non-universal. And this has been done in many hundreds of papers in the archive. That was the past. Now, how is done in the present? In the present, people is taking more carefully the problem and is doing this expansion in an effective field theory. And one of the possibilities is this one. So you can really produce all these Wilson coefficients and everything, and try to do the matching and all they have to do, and try to test the effect on neutrino experiments. There is one paper that is very good, been successful in testing this in reactor experiments, right? I have an example I can give you, but still, I think it's a field that is growing. Is kind of probably is the natural way of accounting for NSI. Instead of doing it like phenomenologically, you do it properly with within an effective field theory framework. So this is an open field, and you have some operators that will impact neutrino oscillations.
Any more questions?
Maybe I should read your paper, but you mentioned about the neutral current thing.
In the steroid, right?
That's check the oscillation probability add up to 1 or smaller than 1.
Okay.
Can you tell me more about that? So what is the experimental setup and what is the measurement?
Okay. The analysis of the steroid with the neutral current in June. Yeah. Let me I was going back. Okay. Okay, here we are. Some part of the information is here. This is the main physics, but here are the results. So basically, in this analysis that was done in 2017, so quite some years ago, we assumed some setup for June. So the standard setup at the time was 40 kilotons of liquid argon in the effective volume. We assumed in this work, we didn't take into account information from the near, only in the far, right? But for the neutral current is enough to account only for the far detector, right? The sensitivity can be destroyed because there are many cancellations happening for different values of the new delta CP phase. This at that time, in any of the previous papers, wasn't mentioned this, right? The idea was not original because this has been done previously in NOAA and in many other papers in -2. But for the first time, we did all the math properly, and we noticed that there are several cases where the sensitivities are lost depending on the new phases contributions. So this is one of the main messages of our paper. And you see, this is the comparison of these two plots. So there is one thing that is destroyed, the cancellation happens for this kind of if the delta m squared for one is smaller than the atmospheric one, right? What usually all the papers do is they go to the high part, be above the atmospheric, and everything works well, and they can put a stringent limit in the parameter space. This is usually done in NOVA, Super K, Ice Cube. At that time, that was the best experiments concerning this parameter space. So charge current also contributes to the constraining the full parameter space. So in principle, you should do a combination of both charge current and neutral current, right? And this is what collaborations should do and will do, right? But the sensitivities of the extra mixings depend differently on the information. So charge current information is good for this kind of channels, and neutral current information is good for these other two parameters. There is no better handle on these parameters. So in fact, the title of our paper is that we have constrained the esteral tau mixing, because we imagine the following situation. When Dune starts running, probably all of the experiments will constrain more the parameter space of all the parameters, but they will not be able to constrain very well the tau, the mixing with the tau, because the tau neutrinos in an experiment are very hard to measure. So assuming this situation, we say, okay, let's see what Dune can do for the 3-4 parameters. That was the motivation of our paper, and we found these cancellations. So I can give you even more details if you want. I don't know if that was your question. That was your question?
Yeah.
Okay.
Questions?
That it will be a technical study of connection between oscillations and Dark. Do you have an idea of what kind of process with Dark can sustain?
Okay, the direct connection with dark matter, I mean, there is not that direct connection of dark matter and neutrinos in a neutrino experiment, but there are several works since neutrino due to this process, and also in dark matter scenarios. You know that experiments are dark matter direct experiments are reaching a sensitivity where they have not seen anything, you know, and then they are reaching the neutrino floor. So many people is saying, okay, we will found dark matter experiments that are very expensive to found nothing. And so neutrino physicists, we are saying, no, you can do many neutrino physics with dark matter experiments. So it's in this sense, that is the connection with dark matter, but not from the model building point of view. Good.
Yes. Regarding one of the model with the extra dimension that you will mention, that you have those two extra dimension with a hierarchy between the compactification ratio. How much is the hierarchy that you take for the compactification ratio? I suppose you're taking flat extra dimensions, right? Or you're also considering one dimension and flavor.
In principle, you can consider any number of extra dimensions. But the important thing is that one of them should be larger than the other. This is the only.
So how many order of magnitude you're considering?
Okay, this is a difficult question, because in principle, what is done in this vanilla LED model, probably you can read Davodia's paper. This is a very nice, this is the best paper ever with the idea, 2002. But basically, if you can have any number of extra dimensions. If one of them is the largest, then you can build an effective theory of 5. 4 plus the one larger, you have an effective 5-dimensional theory. And this is enough to have all these phenomenological consequences. But it's different if all of the extra dimensions are of the same order, because in that case, what is constrained is the volume of the compactification. And the best experiment to do this probably is the LHC or astrophysical from astrophysics, but not neutrino experiments. So neutrino experiments are only competitive in this kind of scenarios where the compactification is the reason of the L here, right? The largest dimension. One of them has to be the larger, Otherwise, your compactification radius is even more constrained than this scale, I guess, right? So here we are constraining micrometers compactification radius.
Thank you.
Okay, wait.
More questions? If there are no more questions, we say David for the very nice and very complete seminar. Thank you so much, David.
Thank you. Stop the recording.
Yes, I don't know. Stop.
There's one chat.
There is one question in the chat, right?
No.
No.
Se ve bien.
Stop.
Dejar de